Hi everyone. How are y'all doing today? Um, so I need to start today by just giving a massive apology to everyone for the insane clusterfuck everything's kind of been recently. The issues with the quiz and the homework this weekend. Very sorry about that. I could have sworn I um, that I added the the submission thing for the homework, but apparently I did not. So that's I've extended the due date to the end of today for the homework for homework 2. It should be, let me triple check. Should be updated now. So you could submit like you submitted homework 1. Let's make sure. Looks like we already got some submissions. That's good. Yes. Okay. Yeah, my apologies, guys. I mean, there's no good excuse, but things have been completely insane recently, and it's more or less calmed down. I'm gonna spend basically all of today taking care of the backlog of grades, and that should be done by the end of today. Also, so for the Achieve homework, I am going to be opening up the older ones. If you have some unused attempts on problems that you haven't either haven't done or got wrong, but still have some attempts, you should be able to go back and do those. Also, I will be dropping one of the learning curves that we did before when we were doing learning curves. And 2 of the homeworks. But I will have to export those and have those done myself, because I can't do that, unfortunately, inside Achieve. And yeah, so that's anything else? Yes. So I'll be dropping the lowest 2 homework scores. And yes, so after class, I'll be opening up the old assignments. I have to because we have like very little control. If like basically all the batch editing and everything that can be done can only be done by the course coordinator, who has like master level access to the course. So I got to go individual assignment by individual assignment and open it up. But I'll do that today. Yes, so the 2 lowest homework scores and then the 1 lowest learning curve I will drop. Yes, anything else? I believe that's it. Well, once again, I'm really sorry. No good excuse for the disorganization recently, but yeah. Anyways, let's finish up talking about Stokes' theorem, which once again is probably the most complicated material in the entire course. Really a lot going on with any Stokes' theorem problem. Oops. Okay. So just a reminder what Stokes' theorem is. If we have a surface S, so we have an oriented surface S. So oriented means we choose the positive unit normal. So it's either going to be pointing on one side or the other side. So given an oriented surface S in R3, the boundary of S, which remember, so the boundary of S could consist of one curve, two curves, multiple curves. But each of those curves we orient. So if there's one curve, which is often the case, so if the boundary of S is just one curve, we can use the right-hand rule to give the boundary an orientation. So for example, if this is our surface S, we have, let's say we give it the negative y pointing normals for S. So we need to orient the boundary curve here. So the boundary curve consists of one, or the boundary of S consists of one curve. So there's a nice trick we can use, which is the right-hand rule. So basically just take your your right hand, point your thumb in the direction of the normal vectors. So it just needs to be like a general direction. If there's this really only works if there's one boundary curve in boundary of S. But so in general, they're pointing towards the negative y and the negative y direction, and then your fingers curl inwards in the direction of the orientation of the boundary curve. So I'm pointing my thumb in the negative y direction. My fingers are curling around like this. And so that's going to be the orientation of, let me use a different color there. That's going to be the orientation of our boundary curve, right? We're going around like this. And so that works if you have one boundary curve. If you have more than one, or you don't like that, you can stand on the boundary curve. See, it's kind of easy to understand this, but it takes like an hour to write down, unfortunately. But you stand on the boundary curve, the trick for orienting these guys, with your head in the direction of the positive unit normal vector, right, on S, because we've given S an orientation. And the direction the orientation of each boundary curve is given by doing that and walking so that S is always on your left. So for instance, if this is our cylinder, we have a cylinder here, that's our surface. And suppose we're given the outward pointing normal. Our boundary consists of two surfaces, the front circle and the back circle. And so let's use this rule to orient them. So for our front circle, here we are, right here. Beautiful. With our head pointing, standing on the edge with our head pointing in the direction of the positive unit normal vector. That is the side that the surface S is on. And so we want that to be our left. And so if that is our left, we're walking around in this direction. Is that even, sorry, that is not terribly easy to tell what direction that is. Hang on. We're walking around. If that is our left, we're walking in this direction. So if we're looking straight at it, we're going around clockwise, sorry. And then if we play the same game on the other side, we see that we would be going around the opposite direction. It is very difficult to do this with my finger. My apologies. And that is how we orient our surfaces. Okay, I don't want to spend too much time because we really need to do examples and we need to kind of talk about how we understand what's going on with these problems kind of conceptually. Okay. So if we're given an oriented surface S, let me just say with positively oriented. And when I say positively oriented, I mean oriented according to the rule we just said. So the boundary curves, boundary of S, are oriented according to the rule we just said. Then Stokes' theorem says the integral of a vector field F along the boundary curve, so these are line integrals because they're over curves, that is equal to the integral over the surface S of curl of F. We can think of curl of F as being the derivative of F in this sense. So we can integrate a vector field along the boundary curve, or we can integrate it, the curl of the vector field, the derivative, over the surface. And those are going to be the same. And remember, curl of f is what we check to see if a vector field is conservative. And if we're integrating conservative vector field f over a closed curve, we know that's always 0. And so the curl of f is going to be 0 for conservative. So clearly, in this case, if the curl of f is 0, if f is conservative, then we're integrating 0 over the surface, and that's going to be 0 too. And so that's how you remember what we're integrating. Curl of f is the thing you check to show that's conservative. Similarly, if your surface is closed, then there's no boundary. The boundary is empty. And so if we use this theorem, we see that we're integrating f over nothing, really, over an empty set, which is 0. So if S is closed, then it doesn't matter what f is. If you integrate the curl of a vector field, no matter what, you always get 0. If you're integrating over a closed surface. But that's only if S is closed, and that's only if the thing you're integrating is the curl of a vector field. Okay, so that's Stokes' theorem. It's like Green's theorem for R3. We can go from an integral of a vector field over the boundary curve, or we can integrate over the region S, the surface, the derivative, which is curl of f in this case. Okay. So let's do an example. The thing about Stokes' theorem is, unlike Green's, Green's is really only one direction. We really only go from an integral over a closed curve to a double integral. That's really the only direction we generally go with Green's. We saw area, but that's unusual. With Stokes, we can kind of go both directions. So we can go the integral over a closed curve in R3 of a vector field. We can turn that into a surface integral of the curl of the vector field, where we either need to find a surface where our curve is the boundary, or we're given that the curve is the boundary of the surface. So let's look at an example where we go from a line integral over a closed curve to an integral over a surface using Stokes. So let's evaluate the integral over the closed curve C of the vector field f, where here C, nope, sorry, give that a sec. Our vector field f is going to be not particularly nice. This is pretty common in Stokes' theorem. So sine of x squared, e to the y squared plus x squared, and z to the 4 plus 2x squared. So that's our vector field f. Already not looking nice. Luckily, Stokes' theorem can save us here. And C is the triangular path and I'll give the vertices in the order we go. So we go from 0, 0, 1 to 3, 0, 0. Yes. 2, 0, 2, 0, and then back to 0, 0, 1. The location I wrote these here is unfortunate. That's not actually the shape, but these are the vertices in the order we go around them. So that is a closed curve in R3. And we're integrating a vector field over it, so we can use Stokes. Notice, first of all, if we try to evaluate this line integral directly, well, let's sketch a picture first and then see what's happening. Okay, so always a good idea to sketch the thing you're integrating over. So our vertices are 0, 0, 1, 3, 0, 0, oops, and 0, 2, 0. And we need to be mindful of our orientation. And so that's the way we're going around this curve here. Okay, so if we try to evaluate this directly, two things. We need to parameterize every single one of the edges separately. And so we're going to have to calculate 3 line integrals because we had to parameterize the 3 pieces separately. Secondly, the vector field is disgusting, and it looks like we're likely not going to be able to evaluate this directly. So those are both dead giveaways that you probably want to use Stokes. But really, if you're integrating over a closed curve in R3, you should be thinking Stokes immediately. Okay, so in order to do Stokes, right, so Stokes says the thing we want to evaluate, this is our curve C. What we need to do is we need to turn this into the double integral over some surface S over the curl of this vector field. So we need to find a surface S where the boundary of S is equal to the curve we're integrating over. Okay. So in this case, there are infinitely many surfaces we could come up with which have this triangular thing as the boundary. Infinitely many. But there's a very obvious simplest surface. What kind of surface could we think of that has this as a boundary? It's going to be a piece of what type of surface? It's just like the simplest surface we have in R3. Right, it's going to be a piece of a plane. Often we'll be able to do that, and that's usually the easiest thing we can do. If all 3 of those points lie, well, that's 3 points. You can always find a plane which contains 3 points. But yes, if all the curves lie in a plane, we can do that. Okay, so first we need to find what plane this is. So that's thing 1. And then we need to give it an orientation, and then we'll put that aside. But okay, so what is our plane? So we know the plane contains the points 1, 0, 0, sorry, 0, 0, 1. Let me just call these P, that's an R. So P, Q, and R. And so what we could do, if you like, is you could look at the vector PQ and PR, take the cross product to get the normal, and then do that. Or since these are vertices, so that's perfectly fine. So PQ cross PR. Or we could say we know it's going to be let's put it in the form AX plus BY plus CZ equals 1. And then let's use our points to figure out how we do this. It's really easy because those points lie on the coordinate axes where only one of the variables is non-zero. So that's nice. So we know we have the point 0, 0, 1. And so plugging in 0, 0, x equals 0, y equals 0, z equals 0, we see c has to be 1. Plugging in 3, 0, 0, we see a has to be 1/3. And plugging in 0, 2, 0, we see b needs to be 1/2. So we have the plane 1/3 x plus 1/2 y plus c equals 1. And that's our surface. We could also do that by taking the cross product of PQ and PR. But yeah.
Professor, and you got these A, B, and C from plugging in one of these points, correct? This probably the 0, 0, 1, and then.
Yeah.
Okay.
So this is a nice way to find the equation of a plane. We can always put it in this form as long as it doesn't go through the origin. That'll be fine. And yeah, especially if we're given points on the coordinate axes where 2 of the variables are 0, it's really easy to solve for A, B, and C in this case. But that's a nice shortcut. Okay, so we have a piece of this plane there. That's our S. So let's find let's give it an orientation also. So is it going to be upward or downward pointing normals? So we need to orient our surface. Okay, so what we're going to do is we're going to use the right-hand rule kind of in reverse, right? So take your right hand and curl your fingers inwards in the direction you're going along the curve. When you do that, your thumb points in the direction of the normal vector. So you take your right hand. Here we go. We're going around this curve like this. So is your thumb pointing upward or downward? It's pointing up, right? When we do that. Okay, so we'll keep that in mind. All right. So all right. So we are calculating the integral over the surface S, which we just found, of the curl of F. And so we need to go through the whole process here. First of all, let's calculate the curl of F. And I'm just going to go ahead and tell you what it is. Remember, the curl of F is just del cross F. That is going to be 0, negative 4x, 2x. And so that's really nice. That definitely cleans up the thing we're integrating, because it was disgusting before. But this is a relatively simple vector field. So we need to parameterize our surface S. So our surface is a piece of a plane. So that plane, we can write as the graph of a function. We can get z by itself. So we can isolate z. And write it as the graph of g of x, y, a function of x and y, 1 minus x over 3 minus y over 2. So we know how to parameterize graphs of functions. We let x be x, y be y, and then z is 1 minus x over 3 minus y over 2. Whoops, no comma. And x and y are going to live in the region D, which is just the projection of this to the xy plane. So just look at the shadow of this guy in the xy plane. So just take all your points, drop them directly down onto the xy plane if they're not there already. And so D is going to be this region here, where x and y live. Okay, I'm moving through this rather quickly, but all right. So we parameterized our surface S. And we know ds is going to be, oops, that cross product guy. Remember, it's either g sub x cross g sub y or negative of that. And we already said this has to be the upward pointing guy. Remember, that's the cross product thingy. So we have the graph of a function. We should have this memorized, what this looks like. So remember, if our surface is parameterized like this, it's the graph of a function. So we let x be x, y be y. Z is whatever our function g of x, y is. Then our upward pointing normal is going to be negative derivative of g with respect to x, negative derivative of g with respect to y, 1. And that's our upward pointing normal because the z component is positive. It's 1. If we wanted the downward pointing one, we would flip everything, take negative of this. So for us, remember our g was 1 minus x over 3 minus y over 2. And so our normal is negative derivative of that with respect to x. So negative 1/3, which is 1/3. Negative derivative of that with respect to y, which is 1/2. And 1. because we want the upward pointing one. Okay, so putting this all together, so we replace x, y, and z in our vector field, so in the curl of f with the parameterizations. We integrate over D where x and y live. So the curl of f we said was 0, negative 4x, 2x. So replacing x, y, and z with their parameterizations, well, the only thing that shows up is x, and x is equal to x in our parameterization. So we get 0, negative 4x still, and 2x still. That's the curl of f. And then we're dotting that with the normal, or the n, rather. 1/3, 1/2, 1. And when we take this dot product, we see we get 0 minus 2x plus 2x. So we're just integrating 0. So we see our integral is actually 0 in this case. Okay, so there was a lot that went into this. And so let me rewind a sec and let's remember what we did here. Okay, so we needed to evaluate a line integral of a vector field over a closed curve in R3. Usually integrating a vector field over a closed curve in R3, that should tell you, you should probably use Stokes here. This curve, this closed curve, is going to be the boundary of some surface. And so we're going to use Stokes to turn that line integral of the vector field over the curve into a surface integral over some surface where this curve is the boundary of that surface of the curl of the vector field. Okay, so first thing we had to do is we had to find a surface where this curve is the boundary of that surface. There are infinitely many choices here. We'll talk about this in a sec. But the simplest one is just this triangle just lies in a plane. So this is just a piece of some plane. So we had to find out what that plane was. And there are different ways to do it, but we know how to find the equation of a plane. And we found the equation of our plane here. Okay, so we have our surface. We had to give it an orientation using the right-hand rule, sort of in reverse. We saw it had upward pointing normals. Okay, so now we've turned that line integral into a surface integral of the curl. And so we forget everything that happened before. Now we're just evaluating this integral. We have our surface, so we need to take the curl. Then we need to do as usual, parameterize our surface. It's just the graph. We can do it as the graph of a function by getting z by itself. And we find the gx cross gy, or negative of that, depending on our orientation of our surface. We saw it was upward pointing. We know how to find the normal for the graph of a function. You should have that memorized. It's nice. And then we evaluate. And then when we evaluate, we see we're just integrating 0.
Since this was closed already in the beginning from like the graph, wouldn't we know that the curl would have been 0? Kind of like what we learned earlier.
No. So what does it mean for a vector field if the curl is 0? What can you say about the vector field?
it's conservative, right?
Exactly, right. But most vector fields are not conservative. In fact, this vector field's not conservative because when we take the curl, we see that we don't get 0. We get, this is the curl. So this is not a conservative vector field. So we can't automatically say that the integral is going to be 0. If it is conservative, the integral over any closed curve of a conservative vector field is 0. But this is not conservative, so it's not necessarily going to be 0. This example works out so that the integral is 0, but it doesn't have to be. Does that clear that up?
Yeah, and then just to like go over it, where did we get the 1/3, 1/2, 1? Like
okay,
the
so there
n
are
of
different
x,
ways.
y?
Basically, we decided that, okay, this triangle lies in a plane, so we're just going to find the equation of that plane and let that be our surface. And there are different ways to do this, right? If you have 3 points and you want to find a plane containing those 3 points, P, Q, and R, you can look at PQ cross PR, if you like. And you'd probably get something like, you can multiply everything by 6 and you'd get like 2, 3, 6 or something like that. That's probably what you get. And you could find the equation like that by taking the cross product of those guys, finding a normal vector. This is kind of a shortcut you can use if you just have like 3 points on the coordinate axes. You can say it's like ax plus by plus cz equals 1, and then solve for a, b, and c by plugging in your points individually. It's just kind of a shortcut, but if that doesn't make sense to you, then.
Okay, I see that. And then that's where you get that 1/3, 1/2, and 1 from. And then, like you said, you can multiply that by 6, and we would have got 2, 3, and 6 there.
Yeah, that's probably what would happen if you take the cross product.
Okay, perfect.
Yeah. Okay. All right, so lots going on with these problems. Okay, another thing I want to mention is, so sort of conceptually, some things you need to understand about Stokes' theorem is the following. So remember, for the fundamental theorem of line integrals, I think I called it the fundamental theorem of line integrals. So basically, line integrals of conservative vector fields. So if f is conservative, in other words, if it's the gradient of some potential function, little f, so it has an antiderivative. So we can think of little f as the antiderivative of the vector field f in this case. You can think of the gradient as taking the derivative in this case. So if you have some curve from P to Q, and we are integrating a conservative vector field, all that matters are the endpoints, P and Q. And in fact, if we have 2 curves, C1 and C2, with the same endpoints, P and Q, so if f is conservative, if we have 2 curves with the same endpoints, the integral of the conservative vector field over those 2 curves is going to be the same. Because by the fundamental theorem of line integrals, those are both equal to the antiderivative at Q minus the antiderivative at P. So we can think of the point Q and the point P as being the boundary. And we give it an orientation. We say endpoint minus starting point. So these two curves have the same boundary. So if you're integrating a derivative over either one of them, you're going to get the same thing because they have the same boundary. All that matters when you integrate a derivative, in this case, the gradient of a function, is the boundary. If two things have the same boundary, integrating a derivative over either one of them is going to be the same. So we saw that with line integrals. The same thing is true for surface integrals. And we can show that using Stokes' theorem. So if we have two surfaces, suppose this is suppose that is surface 1, and say this is surface 2. And our boundary is just that guy there. So we have two different surfaces, but they have the same boundary. And we need to be mindful of orientation here, but they have the same. If we take the boundary of both and looking at the orientation, we get the exact same curve. These two guys both share a boundary. They're two different surfaces, but they have the exact same boundary with the same orientation. Okay, so by Stokes' theorem, if a vector field is the curl of another vector field, let me write it like this. If we integrate a derivative over either of these surfaces, so think of the curl as being a derivative, we're going to get the same thing, even though they're two different surfaces. Because by Stokes' theorem, both of these guys are just equal to, I should give myself more room here. The integral, let me just call this C, over the boundary curve, which they both share, of f, which we can think of as the antiderivative in this case. So this is exactly what we saw with the fundamental theorem of line integrals. If you're integrating a derivative, right, in this case, the curl of f, then it doesn't matter what surface you're integrating over. All that matters is the boundary. So if you have two wildly different surfaces with the same boundary, if you're integrating a derivative over either one, over both, they're going to be equal because of Stokes' theorem. So integrating the curl over any two surfaces that share a boundary is going to give you the same thing. Okay, so I'm probably going to try to do another Stokes example because this is the hardest stuff on Wednesday. But let me sort of give a summary of everything. So if you're an R3, if you have some closed curve C, here's how Stokes works. So you have the line integral over some closed curve C of a vector field. You should automatically be thinking, you should use Stokes to turn that into a double integral over the surface. If it's not a conservative vector field. If it's conservative, then obviously the integral is 0, but we're probably not going to give you something that easy. So with Stokes, you can start off with a line integral over a closed curve. So we're either told that closed curve is the boundary of some surface, often we're not, or you need to find that surface. So we need to find some surface that has this closed curve as the boundary, and then we need to integrate the curl of f over that surface. That is one way Stokes can be utilized. Starting with a line integral over a closed curve, turning it into a surface integral of the curl of the vector field over that surface. But often we need to find that surface, or we might be given what that surface is. Or 100% of the time, if you see that we need to integrate over some surface S, the curl of a vector field, if you see we're doing the surface integral of the curl of a vector field, that should be a dead giveaway. That should scream out to you. Use Stokes. So if you see we're integrating over a surface, the curl of a vector field, 100% of the time, every time, use Stokes. So we're going to turn that into a line integral over the boundary of the vector field f. So Stokes can go either direction. You can start off with a line integral over a closed curve, and then turn that into a surface integral of the curl of f. Or you can start off with a surface integral of the curl of f, and if you see the surface integral of curl of f, 100% of the time you're always going to use Stokes' theorem. You turn that into a line integral over the boundary of f. And going a wee bit over here, but I just want to emphasize this because it's really important. So if f is a closed surface, the boundary is empty, right? There is no boundary. And so the integral of the curl of a vector field, I want to emphasize this. It's only if it's the curl of a vector field. The integral of just any given vector field over a closed surface is not necessarily going to be 0. But if you're integrating the curl of a vector field, it's always going to be 0. Because of Stokes, right? That's like integrating the vector field over the boundary, which is empty. So like a sphere. Like if you have the entire sphere, that's a closed surface. If you have like a cube, just bear with me. Pretend that's a cube. Pretend that's a cube. I'm not even going to draw the that guy there. You could have a cube. You could have say a cylinder, but you have the top and bottom caps on. Right, you have the top surface and the bottom surface. Any of these guys are closed. Anything with a definite inside and outside is a closed surface. And if you integrate the curl of a vector field over any of those, you're always going to get 0. And then also one last thing. If you have two surfaces which have the same boundary and the same orientation, so if the boundary of one surface is equal to the boundary of another surface, so for instance, say this is S1 and this is S2. Using the right-hand rule, we see we would go around this way. Yes, okay. So bear with me. Pretend those are two surfaces with the same boundary. One is like a paraboloid opening downwards with the rightward orientation. The other one's like, I don't know, a hemisphere or whatever with the rightward orientation. So they share the same boundary and they have the same orientation on the boundary. Then if you're integrating the curl of a vector field over either of them, you're going to get the same thing. Because all that matters if you're integrating the derivative over something is the boundary. If the boundary is the same for two things, if you're integrating the derivative over both of them, you're going to get the same thing. And we know that by Stokes, because that's just equal to the integral over the boundary, which is the same for both. Okay, sorry, went way longer than I intended to today, but yeah. Yes, I am. I have office hours immediately after. Like I'm moving over to my office hours like right now. But any other questions? All right. Then I am heading over to office hours, and I will see you guys on Wednesday.